Hello, everyone. I'm Kunhe from UC Berkeley. I'll be presenting our paper about fundamental bounds on online strategic classification. This is joint work with Saba and Avrim from TTIC. Let's first begin with some background about strategic classification. Nowadays, classification algorithms are everywhere. In examples such as loan approval, college admission, and job interviews, many important decisions regarding whether the agent is qualified or not are made by machine-learned classifiers, such as decision trees. These classifier will take the agent's features as input, for example, gender or occupation, and output a label which is either positive or negative. However, it is important to note that the agent's features, which serve as input to the classifier, they are not static. Instead, strategic agents, as we call them, they may try to game the classifier by misreporting certain features at a cost, but such a misreporting behavior does not change the true label of the agent. For example, consider the loan approval example, then applying for more credit cards does not change the true loan worthiness of the agent. However, it could potentially increase the credit score, which may then yield a positive outcome from the classifier. Therefore, the goal of strategic classification is to learn classifiers that are robust to gaming behaviors. In our paper, we study strategic classification in the online setting. Here, we assume a scenario where agents arrive one by one, and their order of arrival, initial features, and true labels are all chosen by an adaptive adversary. At each point of arrival, the learner needs to make irrevocable decisions on the agent's outcome. There are several challenges of the online setting compared to the offline setting. First, the behavior of the agents change over time because they depend heavily on the current classifier. This means that even agents with similar features might behave very differently over time. Additionally, there is no reliable source of unmanipulated data. This is because we don't assume that the initial feature comes from a fixed distribution. Rather, they are selected by adversaries, so they may not demonstrate identifiable patterns. In the above setting of online strategic classification, we ask the following main question: what are the fundamental bounds that separate achievable goals from unachievable ones in the setting of online strategic classification? Now let's delve deeper into our specific model. We focus on the canonical setting of online binary classification from expert advice. Here, the features come from a fixed domain X, and the learner makes decisions based on the advice of N experts from a fixed expert class H. To model strategic agents, we assume that there exists a strategic manipulation graph that underlies the domain X. In this graph, each edge represents a potential manipulation. An agent with a specific set of features could misrepresent as another set of features if it helps for them to receive a positive classification. The strategic manipulation graph model was first proposed by John and Conitzer in 2021 and studied in the offline setting by Leshner and Erner in 2022. We have chosen to use this model for several reasons. First of all, it could reflect the agent's bounded manipulation power because not all two sets of features are reachable from each other. This model could also model arbitrary feasible manipulation sets beyond the ones characterized by LP balls with bounded radius in the Euclidean space. This is in contrast to a lot of previous work that studies strategic manipulation. Finally, this model also allows for arbitrary decision boundaries, which could be nonlinear, non-convex, and so on. To illustrate these points, let's return to our loan approval example. Here we assume that the agent's features are two-dimensional. It consists of the credit score as well as the number of credit cards. So it is clear from this graph that not all pair of points which are close in Euclidean distance are reachable from each other. Instead, the space of feasible manipulations could be very complex. So we consider a few choices, for example. An agent could decide to apply for one credit card, which will cause a slight decrease in their credit score because there's a hard pull. But if the agent's initial credit score is high enough, then it also causes an increase in the number of credit cards by 1. But if not, the number of credit cards stays the same. The agent could also apply for 2 credit cards on the same day. Therefore, they only need to suffer from 1 hard pull. And depending on their initial credit score, the number of credit cards could increase by either 0 or 1 or 2. And the agent could also apply for credit card months in advance. Therefore, the increase their credit score will offset the slight decrease because of the hard pull. Therefore, from this example, it is clear that the set of feasible manipulations is highly discontinuous and also non-uniform for agents with different initial features. Therefore, this example could be more appropriately modeled using a discrete manipulation graph instead of the Euclidean space. Now let's discuss the interaction protocol. We consider an online stackable game with T time step. At each time step, the learner commits to a classifier HT. For example, in this figure, this HT would label all the red nodes as negative and the green nodes as positive. After the learner commits, the agent with initial feature UT and true label YT arrives. The agent could be, for instance, a female chef with true label -1. Upon arrival, the agent could decide to manipulate to a new observable feature VT, and this VT should maximize their utility under HT. Here, the utility is determined by the value of the outcome under HT minus the cost of moving from their original feature UT to the new observable feature VT. For the value, we assume that it is 1 on positive outcomes and 0 on negative outcomes. And for the cost, we first assume for simplicity that it is 1 on each edge, but in our paper, we could extend to arbitrary edge weights. And in this example, after a manipulation, the agent moved to a different set of observable features and received a positive outcome. This leads to a mistake by the learner because the predicted outcome is negative, which does not the predicted outcome is positive, which does not match the true negative label. The learner's goal in this setting is to maximize classification accuracy, which is measured by the total number of mistakes. Here, we don't focus on incentivizing truthful behavior, and our only concern is whether the reported features lead to a correct classification. We compare our results to a strategic benchmark, which is different from the classical benchmark because when we compete to the best expert H star, we assume that the agents manipulate according to this H star instead of HT as they did during the interaction. We denote the minimum number of mistakes made by the best expert H star as opt. We now introduce some related works. The specific perspective of stackable games in learning mechanisms has been developed since earlier works of Davy et al. And Deco et al. For classification problems specifically, the formulation of strategic classification was introduced by Hart et al. In 2016. Since then, There have been a lot of different angles on studying strategic shifts and behavior in learning mechanisms, especially in offline settings. Recent works have brought the strategic classification into the online setting, although they largely focus on the geometric setting in Euclidean space. In contrast, our research focused on the discrete graph setting. As a warm-up, let's first consider the failure of naively extending the vanilla halving algorithm. Let's start with the realizable setting where opt is 0. The halving algorithm is one of the most fundamental algorithms for non-strategic classification. It works by maintaining a version space HT, which is a subset of the hypothesis class that agrees with the historical data. And then on each point, the algorithm label it according to the majority vote of the version space. It then updates the version space by excluding all the experts that have made mistakes. In a non-strategic setting, it is well known that the halving algorithm make at most log h mistakes. However, in a strategic setting, we will show that it could potentially make infinite number of mistakes. To illustrate this, consider a star graph that consists of a central node x0 and delta leaf nodes x1 to x delta. We also assume that the expert class consists of delta experts, where each expert label the corresponding leaf node xi as positive and all the other nodes as negative. So in this case, if the version space consists of the entire hypothesis class, then the majority vote classifier would label all the nodes as negative because none of them reach the threshold for majority. Now let's consider a true positive agent that arrives at the central node. So under the majority vote classifier, because all the nodes are labeled as positive, this agent would stay put at its original place and receive a negative label, which is a mistake. However, if we consider each expert hi in isolation, then it could label the agent correctly because in response to hi, the agent manipulates to the corresponding positive label xi and receive a positive outcome. Therefore, no experts should be removed from the version space. Therefore, by repeating the same agent over time, the vanilla halving algorithm is forced to make an infinite number of mistakes. Next, we present a modification of the halving algorithm called the bias halving algorithm that end up achieving bounded number of mistakes in a strategic setting. Before we introduce the bias halving algorithm, we first discuss an important graph characteristic, which is the maximum degree, and we denote it with delta. This quantity will repeatedly appear throughout the talk. Based on delta, we will make two modifications to the algorithm. The first one is to change the threshold of halving from 1/2 to 1/2 plus delta. This change will encourage the majority vote classifier to assign positive labels. We also modify the update mechanism for the version space. On every mistake, if the agent is a true negative, then we remove all the experts that label the observable node VT as positive. However, if the agent is a true positive, then it means that it is a false negative and the agent hasn't deviated from their original features. Therefore, we consider all the neighbors of the observable point VT and remove the expert only if it labels all of these points as negative. We do this because such an expert would never have labeled the agent correctly as positive. Our upper bound suggests that for the strategic setting, if opt is 0, meaning that we're in the realizable setting, then the above mentioned bias halving algorithm makes at most delta log h mistakes. And if we're in an agnostic setting, then we could apply similar modifications to the vanilla weighted majority vote algorithm, and it achieves a similar mistake bound in the strategic setting. Compared to the non-strategic setting, there is a delta factor of blowup in our mistake bounds. Therefore, this motivates the next question. Is the multiplicative factor of delta fundamentally unavoidable? Our result is that our answer is yes for all deterministic algorithms. In fact, our lower bound theorem suggests that there exists an adaptive adversary such that in the realizable setting, this adversary could force all the deterministic algorithms to make at least delta mistakes. And in the agnostic setting, they can force all deterministic algorithms to make delta times opt mistakes. For proof, we utilize the same graph structure, but with a different sequence of agents that are tailored to specific algorithm being used. Note that in this example, the size of the expert class is relatively small, which is equal to delta. So this means that the omega h mistake bounds are necessary even when the size of the hypothesis class is as small as delta. And this implies that no algorithm could achieve the log h mistake bound as in the non-strategic setting. Therefore, fundamental differences exist between strategic and non-strategic settings. Given that the lower bound only applies to deterministic algorithms, our next question is whether randomness can help the randomness can help the learner to overcome the delta multiplicative barrier. Our answer is yes, but only if the random bits are transparent to the agents. So in the randomized models, we give the learner the power to commit to a probability distribution over classifiers. Correspondingly, in the interaction protocol, we need to distinguish two scenarios. One is that the agent, when the agent manipulates, it responds to the distribution over classifiers. And another is the agent responds to the true classifier, which is realized from this distribution. And this difference turns out to be important. So when the agent responds to the distribution and random choices are realized after the agent's response, we demonstrate that it is equivalent to consider the induced value on each vertex, which represents the probability of being classified as positive under this distribution. Here, we call this value fractions. Therefore, this model is called the fractional classifiers model. However, when the agent responds to the realized classifier from this distribution, we can no longer make this simplification. Therefore, we refer to this model as randomized algorithms. Our results reveal that for fractional classifiers, the delta barrier still exists. But for the random algorithms model, if the random choices are made after the agent's response, then the learner can successfully overcome the delta multiplicative barrier and achieve a vanishing Stackelberg regret. Interestingly, these results show that the learner actually benefits from being transparent to the agent about the random choices being made. This is kind of surprising because in a non-strategic setting, the learner benefits from hiding the random bits from the learner as long as possible. The learner benefits from hiding the random bits from the adversary for as long as possible. So the intuition behind this is that in a strategic setting, the learner and the agent are not fully opposing. In fact, they could collude so that they compete with the adversary. And this suggests that the utility between the learner and the agents can align to a certain degree. So going back to the previous question, we have shown that randomness can help the learner to overcome the delta multiplicative barrier, but only if the random choices are made before the agents respond. And going back to the main question about the fundamental bounds that separate achievable goals from unachievable ones, our answer is that the maximum degree delta captures both the manipulation power of the agent and the learnability of the problem itself. Finally, we have some open problem. The first one is to close the gap of delta log h between our upper and lower bounds. It's also interesting to derive a mistake bound in terms of other characteristic of the manipulation graph besides the maximum degree. And another question is to obtain lower bounds for the randomized algorithms.